also works. So first of all, I thank very much the organizers of this conference, particularly to Professor Boyle, for giving me an opportunity to hear and talk something about this topic. So this is introduction. So as Shiba pointed out in his book, and also mentioned in the morning talk, so following facts are false. When a manifold M is equipped with an affine structure, so that is equivalent to giving the flat connection or the class of affine coordinate system theta I, then on the tangent bundle, a complex structure is introduced. And furthermore, if M is given a Hessian structure, that is the pair of the affine structure, Riemann geometric, and the complex function size such that this relation holds, then the tangent bundle is given a Kähler structure with a Kähler potential psi theta. So please note that this Kähler potential is just as Hessian potential, and also the variable only depends on the real so the real coordinate system theta. So the aim of my talk is to give a similar situation will appear in the context of quantum estimation theory, where a manifold will be replaced with classical quantum exponential family, and the tangent bundle will be replaced with a complex projected space. That is the set of quantum states. So let me begin with a quick review of classical information geometry and exponential families. So let X be a finite set which represent a sample space. And the script T denotes the totality of probability distribution, small p, which takes values strictly between 0 and 1 and some 1. Now, suppose that some manifold M of this total space is given with a coordinate system theta, for which the element p theta is represented in this form. So this is an exponential family with the potential function of psi theta. So here we assume that the set of F1 through Fn together with the constant function are linearly independent, which ensures that the parameterization is injected. So on the manifold M, so we have the following structures. So first, the Fisher information metric is defined like this, and for which the primary inequality holds for any unbiased estimate. So V is the variance squares matrix of the estimate. So also we have E connection and ion connection, the pair of ion connections. So for which theta I is an affine coordinate system of the E connection, while the expectation parameter defined like this forms an affine coordinate system of the other connection. Then it is now well known that the following duality holds, that this relation holds. And so as a consequence, exponential family equipped with this information geometric structure is dually flat. And also note that eta hat, so that is the n Pavlov as a statistics is an estimator achieving the primary value. So it is sometimes called an efficient estimate. Another remark is that the total space P itself is an exponential family. So that is dually flat. And more important is that any for any exponential family n included in P, the periodic flat structure of the n can be regarded as obtained from the structure of P. So something inheritance. Okay, so that was the quick review of the classical information geometry. And so let me proceed to quantum. Let H be a Hilbert space with an inner product of this, and whose dimension is assigned to D. And define L of H to be the totality of linear operators H, and L sub H or capital H is the totality of Hermitian operators. S bar denotes the totality of density operators. That is a Hermitian operator rho, which is non-negative definite with trace one, is called the density operator. And S bar is the total set of such density operators. In quantum physics, this is the set of states, possible states of the system. Now we decompose this set into the sum of SR by rank. That is, SR denotes the set of density operators having rank R. Then when R ranged from 1 to n is, this is mistake. N should be D. So this is the dimension of H and the maximum value of the rank. So in the sequel, we mainly treat S1 and SD. Okay, now, so suppose that we are given a manifold n of this form lying in the total space S bar. Then we see that a Riemannian metric G can be introduced on n. Okay, so let L theta I be a Hermitian operator such that this equation, which is called symmetric logarithmic derivatives or SLE quotient. So then the Riemannian metric Gij on the manifold M is defined by this. So this metric was first introduced in the quantum extension theory. The metric G is a quantum version, can be regarded as a quantum version of the Complexification metric, and is called the SLE metric. Quantum version of primary inequality, that is the variance covariance matrix of an estimator, is larger than or equal to the inverse of this metric matrix. So that was established by Helmstrom. And also, then Spetz showed that the SLE metric is the minimum among all non-home metrics, but we'll skip this. Now, every SR, so R is the rank, becomes a Riemannian space with SLE metric. So, but as mentioned before, so in the sequel, we focus on the case of R is 1 and R is D. So when R is D, SB is the set of non-singular density operators, which are often called faithful states. Then SD is an open subset in the affine space of Hermitian operators having trace 1. This is affine space. So affine space has a canonical connection, so that is induced on SD. So we call this the M connection following the classical one. So now we have the M connection, mixture connection on this space as the natural flat function. And also note, recall that defined as the dual of this M connection with respect to introduced G by this formula. So this E connection is not flat. So it's only have vanishing curvature, but the torsion appears. This is a quick review of the geometry of SD. So later we so in the case of R1, S1 is a set of pure states. So the set of pure states is regarded as the complex projective space. That is, let us consider the set H. So that not include zero. And for elements Z1 and Z2 of this set, define the similarity condition by this relationship by this equation. Then the quotient set is called complex projective space. So the SLD metric G on this space is known to coincide with the well-known fully distributed metric on the projective space. So now let us see some fundamental facts about the complex structure of this projective space. First of all, one wants a field J satisfying the square is -1. That is almost complex structure is canonically like this for an arbitrary homomorphic coordinate systems. And the G finished metric or so SLD metric is such as this relation. So such a metric is often referred to as a Hermitian metric on a complex manner. And a differential two form omega is defined by this. And furthermore, G is a scalar metric in the sense that omega is a simply form. That is, the omega is equal to 0, or equivalently that there is a function with a potential f satisfying this relation. So, so of course, if so these are written in all the textbooks of treating complex geometry, but defining this symbol, we need something about the complexification of tangent spaces. So instead, we give concrete elementary representation of about what scalar potential means. So let AJK and BJK be defined by this relation. That is the metric of the natural space of the given homomorphic coordinate systems like this. And then F is a scalar potential if and only if this relation holds. Enough. So now let us consider a kind of quantum exponential family. So M as a manifold M of the total space is called a quasi classical exponential family, or QCEF for short, when it is written as this form. So where Fi, F1 through Fn are commuting Hermitian operators, and these operators are assumed to be linearly independent, which assures the injectiveness of parameterization again. And psi theta is written like this, which assures that the trace of cos theta is 1. So on such a manifold M, so EM, first, such a manifold M, of course, SLE metric is given so that M can be regarded as Riemann manifold. In addition, EM connections are defined by requiring that the affine coordinate theta I to be the affine coordinate of the E connection, while theta I, which is defined by this relation, is affine coordinate system of M connection. This is the definition of the M connection here. Then MGDEM is shown to be dually flat, and where G is the SLE. So in the case of some manifold of SE full-length space, then M is equal in SE, and so such induced G, such defined such defined information geometrical structure on M is induced from that of the total space. But this is a special case of the rank. So also this has some meaning, some significance in the complexification theory in that. So the M tuple of F is an estimator for the coordinate system eta 1 to eta n achieving the SLE chronology. So that is the best in success. So let me give some properties of QCEFs. So since Fi are commutative, there exists an orthonormal basis X with the set of small x as three distinct values. And the functions Fi, so since Fi are commutative, so Fi have common eigenvectors, which we denote x. And so denoting eigenvalues by Fi, capital Fi is represented in this form. So now, if we define the probability distribution P theta of x by this, then this can be written like this. That is, P theta forms a classical differential family. And it's easy to see that the information at the dually flat structure of M is equivalent to that of the classical exponential family process. So now, so this slide shows a complexification of a pure state QCEF. So let M rho theta be a coarse classical exponential family of this form, and with the same assumption of Fi as before, that is, Fi are commutative function operators. And suppose that now M is included in the pure complex projective space. And now introduce a complex coordinate system that one to the N like this. So adding a new coordinate yi. And let rho z be defined like this, replacing theta with d. So this is written like this form, that where uy is a unitary operator defined like this. And so rho z is the unitary rotation of the original rho z. So letting be some neighborhood of Rm. N is the dimension of the manifold N, and will be a neighborhood of Rm in Cn, for which the correspondence from Z to rho V is injected. So let me explain some. So this is imagine that this is Cn. And this is Rn, and the theta is the coordinate of Rn, while y is the imaginary axis of dimension n. And originally, the correspondence theta to rho theta is given. So that which maps the Rn to the set Mn, quantum corresponds by exponential F embedded in the projective space. And now, so we enlarge the domain of parameters to some region in this Cn. Then the image is also enlarged in the complex projective space. But note that when so imaginary axis corresponding to the unitary rotation of this projective space. So it passes from bottom along the vertical line, then the trajectory is rotates in the system. So if we take V to the total space, then this correspondence is not achieved. So that we should restrict V to be a some equity. Okay, now, so let M tilde E to the image of the protein, where the ranging over E. Then M tilde is a complex that is holomorphic submanifold of S1 with a holomorphic coordinate system Zi. And hence is scalar manifold with respect to the Ricubini study method restricted connectivity. And when, in particular, when n is d minus 1, that is the dimension of M tilde is that of the projective space itself, then M tilde is open in S1. And so we see 4 times psi theta gives a scalar potential of n. That is the scalar form such as this. So just similar to the case of Shima's observation on n. Okay, the rest is some observation of this set and structure. So let us consider M tilde defined previously, and eta I by eta I is the expectation coordinate. This expectation coordinate system. And y is the imaginary axis. Then this forms a direct coordinate system. That is the scalar form is defined as written in this form. And now, so recall that the E connection and M connection were defined on M, but not on M tilde yet. So let us introduce that. Let the M connection be the first connection with a high coordinate eta I, yi. So that is requiring these coordinates to be affine. So we have one third connection which we call the M connection on M tilde. And so since the Riemann metric GM is given, we can define the E connection as its dual. So then we have this relation. But this is something interesting. That is the almost complex structure and E connection and M connection satisfy this relation, and the scalar form satisfy this relation. So in geometric meaning, so relation to parallel, maybe I should skip. Okay, so parallel and this equation means this commutative diagram. And this relation means this.